Hello, my name is David Riddle. Welcome to our YouTube channel, How to Home Life. Today I'm going to demonstrate how to properly solder various electrical connections and metals together. It seems like I've been soldering all my life. I bought my first soldering iron when I was 8 years old because I was fascinated by electronics and needed that iron to build electrical and electronic projects. I've used the skill of soldering throughout my career as an inventor, designer, and manufacturer of professional tools in the fields of mechanics, electronics, and optics. My soldering skills allowed me to build and market thousands of technical products, such as custom variable power supplies, audio and video equipment, underwater cameras, 3-axis camera cranes for the film and television industry, loudspeakers and mixers for live sound reinforcement, and this list could go on for the entire video. I have also used soldering in repairing countless electronic and mechanical devices. For example, I have reconditioned and repaired thousands of laboratory DC and AC power supplies and resold them on eBay. This was not a hobby. I was able to make thousands of dollars with the money I generated from repairing these power supplies and other electrical and electronic equipment. If you want to be a maker, inventor, manufacturer, or you just need to repair technical devices, this is the video for you. This video is for the beginner who's never soldered before, and also for seasoned soldering veterans. Whatever your skills are, I guarantee you will learn something from this video. I will begin by showing you the basics of soldering tools and techniques. Then I will demonstrate real-world skills in soldering different items such as splicing wires, terminating electrical connectors, building and repairing printed circuit boards, and many more examples. Before we begin the basics of soldering, I would like to ask you to please like and subscribe to our channel. When you subscribe to our channel, it helps us support our videos and allows us to make even more videos. Also, please add any questions you have in the comment section, and I guarantee I will answer all of your questions. And last, if you would like us to make a video on a specific subject, please let us know. Because I'm demonstrating several examples of soldering tools and techniques, this video is longer than our usual tutorials. To navigate through the video, we have divided it into chapters. We did this as you may want to go directly to a certain chapter that interests you. Here are the following chapters. Chapter 1. What is tin and lead solder? Chapter 2. Tools required for soldering. Chapter 3. Flux and oxidation plus soldering various metals. Chapter 4. Splicing single wires together. Chapter 5. Splicing standard lamp cord. Chapter 6. Soldering wires to electrical connectors. Chapter 7. Soldering and desoldering printed circuit boards. We have provided a color-coded graphic at the bottom of your screen that allows you to scroll through the video and easily find the chapter you are looking for. We have also listed the chapters in the description section. The first thing we're going to talk about in this video is the solder itself. Now, John, my producer, is going to jump in with some questions if I don't make it clear. But let's talk about the solder that I'm actually using right here. This is tin lead solder. I do not use non-lead solder, and the reason I don't is for a very good reason. Number one, RoHS, which is R-O-H-S, is a European Union that mandated no lead in solder, but the military has a permanent exemption from lead in solder. Why? Because of the durability of and history of tin lead solder versus all the other formulations that don't have the lead in it.
Well, let me just real quick question. For people who might know nothing about solder, would they say, "Ooh, lead, that's scary, it might hurt me. What if there's fumes, or what if it gets in my eyes?" What do you say to that, Dave?
Well, listen, there is a propensity for young children to suffer from lead poisoning, especially from paint chips and other things like that, but they've allowed solder with employees for more than 100 years, okay? And the most recent health actions have not proven that the solder fumes are a problem. But let's talk about the actual solder itself. This particular solder that I'm showing you today and will be used in all of our demonstrations is a Kester product with mildly activated rosin core solder, meaning that the core holds the rosin and the lead and the tin go around it. The alloy of this particular solder is 63% tin, 37% lead.
And so where is this something you can buy at Home Depot, or is
Generally, no, you can't buy 6337 solder. Generally, you have to buy it online. You simply type in solder 63/37 and it will come up on the Google search.
Why is it not available at Home Depot? Is it some special
Because typically
solder?
the Home Depot is going to sell 60/40 solder. Now the difference between 60/40, 60% tin, 40% lead, is because this particular alloy at 6337 has the lowest temperature melting, coupled with the fact that it doesn't have a plastic state. Now what that means is that when solder goes from a liquid state to a solid state, it goes through a plastic state. This particular solder, being a eutectic alloy, has no plastic state. It immediately goes from liquid directly into solid, not allowing any bad connections, which is typical during the plastic state. And any vibration or anything else, it can cause a bad connection. That's why this solder is very commonly used in most military and other applications.
Okay, everything so far is clear for me, but for beginners, everything's clear except rosin. Okay, why is rosin on there? What is rosin? What does rosin do?
Well, there's different fluxes. First of all, the reason that the flux is there is to prevent oxidation. Everything, 21% of oxygen in the air will affect how the solder works. There's a multiplicity of reasons why rosin core solder is used in electronics. Number one, it's used to prevent oxidation of the joint. And the way it does it, when it melts the rosin, which melts at a much lower temperature than the tin and lead, it covers the entire joint with a layer that prevents the oxidation of the solder. And I'm going to be showing you how not to use solder and rosins that will go bad on the joint. I'm going to demonstrate that.
Is flux and rosin the same thing?
Yes, flux and rosin core flux versus there's acid core flux. There's all kinds of different fluxes available. There's water-based flux, there's solvent-based flux, there's rosin-based flux. They all have different properties and different characteristics, but generally in electronics and electrical applications, you want to be using mildly activated rosin core solder.
Okay, so this is the only solder we're going to use in this video.
This is all of our demonstration is going to be using this particular alloy of solder, the diameter of the solder, which is 0.031 or 32nds of an inch. You will see how it applies to all of the activities that I do in this video.
Does this include when we're going to do sheet metal to sheet metal?
Absolutely. It's all going to be the same material.
So this is going to cover everything.
This solder will cover everything we're going to do. It's called soft soldering. There's hard soldering, which is brazing and silver soldering, but this is soft soldering. And soft soldering is the most common solder used in both electrical and electronics.
Okay, anything else on the solder before we move on?
Yeah, we're going to move on to the availability. Like I said before, just simply Google solder 63/37 and it will come up. Put a quotation mark before the search. Now we're going to talk about soldering irons and soldering guns. The soldering iron that I purchased when I was 8 years old was a traditional soldering iron. It's very much like this Radio Shack version in a Hakko holder, but this is just a heating element and a tip that is heated to melt the solder. Now realize, my father taught me this at 8 years old. He said, "Son, do not melt the solder. The soldering iron is to heat up the material you're soldering to the temperature that solder will melt on it, not dripping it on it. It's designed to heat the object you're doing." That's the key. Now the problem with a simple soldering iron is it has a given temperature. This is a 40-watt iron. That means 40 watts of electrical energy going into it, and it produces about a 600-degree tip. The problem is that may be too hot for some objects. We don't know. I don't know. All I can tell you is that this soldering iron will do any job we're going to do today. It just doesn't have as much control over it. There was an attempt in this soldering iron to have a temperature control. Unfortunately, the temperature control has nothing to do with reality, meaning that it's just a dial and you don't really ever know what the temperature actually is of the tip. I measured this again at full power. It goes to approximately 600 degrees. At low power, it's no more than 200 degrees. So, but unless you have a precision calibrated thermocouple like this to measure the temperature, there's no way that you can figure out.
Describe a situation where you'd want to know an exact temperature and dial in the exact temperature.
Part of the reason is when you're working on delicate circuit boards, very many times you need a lower temperature so that you do not delaminate the copper foil on the circuit board. That's one of the reasons.
Is there something specified on the circuit board of this is the temperature that you're going to use to work on this circuit board?
Typically,
or you just know that?
If you look in active components, they have a maximum soldering time based on that specific temperature that you're going to apply to that component. But the main problem is doing not only assembly but also rework on circuit boards where the higher temperature can destroy the circuit board. And so you really want to have some control. Now,
what's an example of a temperature for a circuit board?
It varies depending on the type of copper clad that's on the board, what adhesives are used. There's all kinds of different things.
So for novices, you could destroy a circuit board if you don't know what you're doing.
Yes, absolutely. Now, one of the techniques that Weller came up with was a temperature-controlled soldering iron. When you change the tip, the back of the tip shows the temperature of what the tip. They come in 600, 700, and 800 degree tips.
So in other words, that specific tip will only go to that specific temperature.
Right. Well, it varies slightly because this is a bistable thermostat in here. The way that this works is from the Curie effect, excuse me. The Curie effect is a phenomenon that Pierre Curie discovered, and that is certain alloys of steel will either attract a magnet or at higher temperatures will not attract a magnet, and that's how this soldering iron works. It basically has a magnet that closes a contact, and when the tip heats up to a certain temperature, on the back of the tip, right here, is a little piece of steel, a special alloy steel that sets the temperature based on the particular alloy of that steel. But that's how this works.
Well, how often have you actually used that?
Well, I actually have used one of these Weller temperature-controlled irons for many, many years, more than 40 years. And they've been around that long. And they are really nice little units. The only problem is that the contacts eventually will corrode, and you have to service these periodically, whereas there's other irons that do not have that capability.
So if you wanted to Google one of these types of irons, what would you Google to find it?
Well, it's
not the manufacturer, but
just Weller. All you have to do is put in a quotation mark and then Weller temperature-controlled soldering irons. And then they will all come up, all the different models. This particular Weller uses a different technology. It uses a thermocouple placed inside of the tip. There's a hole in the tip, and that thermocouple is in the center and goes inside the tip, and then they send that information back through the cable, a multi-core cable, back to a digital display. You can actually set the precise temperature, and it holds it very closely because it's an electronic control instead of a bistable control, that this goes up and down and up and down and up and down and varies in temperature, where this one will control it almost perfectly.
And what's that called? Weller?
This is a Weller temperature-controlled soldering iron. This is just one model. I'm going to turn on this Weller temperature-controlled soldering iron, and you'll see the first message is that's the set temperature that I've set this to, and that's the actual temperature of the tip. And you'll see it start to all of a sudden start moving up. And then this particular soldering iron has what's called a proportional controller that accurately sets the temperature, meaning that you'll notice that it heats up very rapidly right now, and then when it gets closer to the set temperature, which is 605 degrees, you'll see that it slows down appreciably because it uses a proportional controller which doesn't allow overshoot. So they don't want it to go past. That's what the earlier version with the Weller would go past it. But this one, you can see it slows down very slightly, and it's very carefully adjusting itself so it gets to exactly the right temperature. Now, the last thing I'm going to show you is this. This is a Metcal, and this works totally different than these other irons. This one, actually, this box right here produces high power RF energy, radio frequency energy, and then this tip plugs into this iron. It sends the energy, RF energy, down the tip. And again, this also uses the Curie effect by becoming non-absorptive of the RF energy when it gets to a certain temperature. So these tips are interchangeable, and on the tip, they note exactly what the temperature is on the tip. These, not only do they control the temperature very precisely, they also, and it's not variable, it's fixed, they also heat up very rapidly. You can get this iron up and running to temperature within 10 seconds. It's a very excellent soldering iron. The problem is they're quite expensive, and
What's the application for that?
basically more control and continuous use during the day. That automatically shuts down after a period of time.
And what's that technology called again?
That's called Metcal as a manufacturer. There's many other RF power soldering irons that use the technology. Metcal was one of the earliest ones, but Hacko makes them, and I don't know if Weller does, but in any case, that's some of the options. Now, the other option, of course, is a soldering gun. This soldering gun, which I've had also for many years, is basically a shorted turn. This is a transformer with a shorted turn, and it heats up the copper through resistance. And so this shorted turn puts out about 1.5 volts onto this tip, heats it up. The only advantage of a soldering gun is it heats up fairly rapidly, but it doesn't have plated tips unless you buy the special plated tips on these. But the main thing is it can have a lot higher wattage than a typical small soldering iron, because this has the ability to produce a tremendous amount of heat when you're soldering materials. Many times, and by the way, soldering irons come in all different wattages. Soldering guns come in different wattages, and that's what sets the absolute temperature. If you're going to be doing stained glass soldering, that's a totally different experience. Now,
What's the trigger on those guns for?
That turns the gun on and off, as you can see.
But if it's off, is it not hot? The tip's still hot.
No, the tip is hot for a while until it cools down. And then I wait, and you can see this will start to melt solder
Right away.
right about that soon.
Okay. So you still don't want to touch the end of the
No,
soldering
it's
gun
still
even
red
when it's
hot.
off. Okay.
You don't want to touch the end of it.
Now, what's the application for the guns?
The gun, like I said, is for working in where you have a lot of absorptive material that takes the heat away. So it has a tremendous amount of heat capability. That's generally what soldering guns are used for.
Well, tell me, mechanically, what would you be soldering with a gun?
Typically metals to metals.
Oh, metals to metals. Okay.
But you can also do it in electrical. You can do all kinds of things.
So you wouldn't be working on a circuit board with the soldering?
No, you wouldn't be generally working on a circuit board because it produces too much heat.
All right. And do you have to tin the tip of that?
Yes, you have to tin the tip of it.
And you're going to explain that?
And yes, we're going to show that in a matter of
Do you have to
minutes.
tin all of the soldering irons or just the guns?
No, all of the soldering. It depends on what the tips are. Now, there's very inexpensive soldering irons that don't have plated tips. Typically, they're plated with iron, and that iron prevents the copper internally. So you have to use copper to conduct the heat from the heater to the tip, or in this case, the RF energy to the tip. Generally, a heater, the copper is a really much better conductor of electricity, but the copper corrodes because of the fact it's exposed to oxygen. By plating it with, in this case, this is a plated tip right here. This plating keeps this and from oxidizing. But that's one of the reasons that you use plated tips, and exactly to prevent that oxidation of the tip. Because once the tip oxidizes, you can't solder with it. It needs to be tinned.
And viewers, please write your comments in if you have any questions. Are we done on soldering irons? Because I see some other items on the table. Let's go to the heat gun. What's that for?
Okay, well, actually, what I'm going to talk about, the heat gun is for a multiplicity of applications. The heat gun is used for all kinds of things. I have several of these available, and they have in different positions in my machine shop and in my lab and all the other areas because of the fact that they have so many uses. One of the uses in electronics, of course, is to heat shrink tubing. And this heat shrink tubing comes in all different diameters, as you can see. And this heat gun allows that shrink tubing to be slid over the soldered connection and then shrink it. And they also make heat shrink tubing with built-in adhesive that makes it watertight and all kinds of other things. And plus, in our cyanoacrylate video, we showed using crazy glue to actually secure the heat shrink sleeving around the connector.
Right. We'll put a link to that video.
One of the things we're going to talk about is desoldering, and we're going to demonstrate desoldering. Here's some typical desoldering tools, okay? This is a Hakko 808 self-contained solder sucker that has a heated tip and a chamber to hold the excess solder that it picks up. And then I'm going to show you the very tip of it where it has a hollow hole right there, and I'm going to turn it on. You can hear the pump activate. This is an Edson solder pullet, they call it, and this is a spring-loaded plunger that causes a vacuum on the circuit board and sucks the solder off. Not many people use these anymore because these are much more sophisticated. In fact,
so that has a pump built into it?
This is a little spring-loaded pump.
The other one.
No, this has a pump built into it.
Okay.
Okay. This has a manually activated,
and
spring-loaded.
We're going to demonstrate
spring-loaded pump.
Right.
Now the other methodology, this is called solder wick. Now solder wick is nothing more than copper braid that has been saturated with rosin core flux, and because of capillary action, just like in our cyanoacrylate videos, the capillary action causes the solder to flow into the copper braid and suck the solder off of the circuit board. And we'll be demonstrating that also.
Excellent. Okay, the other two devices to your left.
Yeah, well, this is a soldering aid. This is a device that's used to hold pieces of wire or resistors together, or with diodes, or whatever you want to do. It's just a convenient way to hold two pieces of wire. And we're going to be using this to splice two wires together using this device. This device is a tilting clamp on a table clamp, and I use this one with rubber connectors on here to hold objects that I need to solder, whether it be circuit boards, or in this case it's going to be connectors I'm going to show you how to do. I certainly want to talk about the tools one needs to do any work in electrical. This is a semi-flush cutter. This is a flush cutter. You can see that it's perfectly matched sets. And this is a pair of long nose pliers and miniature long nose pliers, but it also has a wire cutter here, and that's a non-flush cut wire cutter. This is a flush cut wire cutter, and this is a semi-flush cut wire cutter. This will do only copper wire. This will do a little bit bigger diameter copper wire. Believe it or not, this little pliers can cut 12 gauge solid copper wire, but I doubt if it'll cut steel. You need a bigger pair of long nose pliers to cut it, or a pair of larger diagonal cutters for cutting steel, and especially spring steel. Now, in addition, you need to strip wires many times. This is a very, very common stripper called a Miller stripper. And they've been used for many, many years. And I use these because they're fairly convenient and they're small, and I can get close to the end of the wire and do this. But they do have one problem, and that is you have to be skilled at using this because of the fact you're going to nick the wire. If you squeeze it too hard, you'll cut the strands of stranded wire, or you'll cut into the solid copper wire, and then that eventually will break. These are automatic strippers that automatically, you just simply place the right gauge wire in this little slot, and that basically allows you to have consistent, non-nicking cuts.
Well, do you have to have, will it do all gauges, or is it a variation?
Well, this particular one goes from 20 gauge to 10 gauge.
So you can adjust it.
Well, there's adjustable little jaws in here that you can just line up the wire that you know the gauge of and strip the wire off. This particular one made by Ideal is a special tool that's used specifically for Teflon wire, because Teflon wire is extremely difficult to strip because of the fact that the Teflon doesn't necessarily sever like PVC or other insulation. So Teflon is tough to strip generally with a Miller stripper, unless you, in this case, you have to hold it and squeeze it carefully, then rotate it 90 degrees or 180 degrees and cut all the way around, and it's very difficult not to nick the wire. This particular one works perfectly because it uses a special die that absolutely will not nick the wire, and it's all laid out here in gauges. And that brings the next step. It's called the American wire gauge. That's how the gauges of wires are specified. The American wire gauge, and they range anywhere from 4/0, which is bigger than my thumb, to extremely fine wire in the 40 to 60 gauge in that wire. So those are typically magnet wires, not insulated wires.
All right. Anything else on the table?
Well, one of the things that I have here is two fluxes. This is a rosin flux, and this is a paste flux, a semi-acid paste flux. This is pure rosin, activated rosin course flux, and this is, you don't necessarily want to use this in electronics unless you can completely wash away the material after the unit has been soldered. And I typically use this for metals, and I typically use this for electronics. In addition,
you'll use those later in examples.
Yes, we'll use those later, and we will show exactly how they work. The other things that I have here are fiberglass brushes. Now, these fiberglass brushes come in all different configurations. This is a typical commercial one that you can buy, and you just simply pull it in and out, and it has a fiberglass brush. Now, you don't want to use a fiberglass brush over your lap, because the fiberglass bristles, which are a whole bunch of very thin fiberglass rods, and they break away and they go in your pants, and then you're going to get itchy, just like working with fiberglass. This one I made using super fine fiberglass. This one has a coarser fiberglass, and then these are available, basically a large rod of fiberglass. The reason we use fiberglass instead of other abrasives, although we do use this Scotch-Brite as an abrasive, because what happens when you use a wire brush, it can contaminate the actual surface you want to clean. You use a wire brush to clean things, but it imparts certain particles of steel into this, and it basically prevents the solder from wetting properly. Now, we'll get into that term wetting. That is to basically flow onto the surface of a piece of metal, whether it be wire or other sheet metal. But cleaning it with Scotch-Brite, cleaning it with fiberglass causes no contamination whatsoever. And so...
Okay, so I think we're done with the table.
Yes.
We're ready to move on to our next chapter.
All right.
Excellent. So Dave, let's go back over a question that I'm not quite sure about, and that's oxidizing, flux, and rosin. And explain, can we see oxidizing, and what does flux do? And just go over that. Let's go, since this is sort of a master class on soldering, let's go deep into this subject.
Well, specifically, we have 21% of oxygen in our atmosphere, and all metals are susceptible to oxides forming because of the oxygen in the air and forming oxides on the surface. Now, different metals, oxide on steel turns into rust, ferric oxide, and then, of course, on copper, you get cupric oxide, which is basically and it turns eventually into verdigris, which is that green color that the Statue of Liberty has. It's a natural oxidizing process, and in the case we're going to demonstrate today, we're going to show some brass. Now, brass is made out of copper and zinc, and these two pieces we're going to use in our demonstration to show how the fluxes act on the oxides that are on the surface. Now, interestingly enough, most oxides are non-conductive and non-wetting when it comes to soldering. Now, that term wetting means, does the solder easily flow onto the surface based on the ability to flow through capillary action and for surface tension onto the copper. And in this case, we're going to be using brass, but the silver is the only material whose oxide is conductive. All other oxides are typically an insulator. So
we want to get rid of oxidizing before we solder, or during the soldering process.
And we're going to show all the different methods you can use to eliminate oxides on the surface. The first demonstration we're going to do, actually, is the difference between mildly activated rosin flux versus highly activated paste flux. And we're going to show the difference between those phenomena, how just without doing any removal, mechanical removal of the oxides, we're going to show just what the flux actually does. What you're looking at is some brass stock that I pulled from my inventory that has been exposed for a very long time to oxygen, and of course it is now oxidized. Now, the first demonstration that I'm going to do is I'm going to add some rosin core flux to this surface by simply taking an X-Acto knife and picking a little bit of flux out of the container and setting it on top. And this is mildly activated rosin core flux. And then I'm going to heat it with a torch, this torch right here, until it melts the solder, or melts the rosin flux. And then what we're going to do is we're going to wipe it off with a cloth, and then you'll see what is remaining of the oxide with mildly activated rosin flux. You see it melts almost immediately, the flux. Yes, and it is flammable. Now we wipe it off. And you can see it's sort of removed some of it, even if that's what mildly activated rosin flux. Now we're going to do the same test with fully activated paste flux. And when we add that, you will see that the effect is vastly more powerful. As you can see, the difference between those two and that. Obviously, this particular flux requires you to completely wash this off because it has acid flux in it. But
so the second one was acid flux.
The second one was fully activated paste flux. And so the difference is sort of cleaning it a little bit versus fully cleaning that copper. And if I wanted to solder that right now, even with rosin core solder.
And I still see some dark.
Well, that's because of the fact I didn't wait
Okay.
for it to completely do
Right.
it. But
the part that's clean is
But
ready.
now what I'm going to do is I'm going to heat it and I'm going to melt solder onto that surface. And you can see it flows perfectly. Okay? Now, what we're going to do now
and that's considered a good joint right there.
well, no, that's just good wetting action. That's
Okay.
what the wetting action is. You notice the solder flows out. Now I'm going to put the surface right now, and you'll see that it does not flow very well.
Oh, okay.
See how it balls up?
Yeah, it's beating up.
Okay, it's not nearly as tough now. If I add more rosin flux to that joint after the fact,
This is the acid or not the acid?
this is the rosin, mildly activated rosin core flux. Now, let's watch the solder balls. And they flow out.
So even with the solder and the flux together, it still works.
Yes.
Okay,
But-
and that's kind of what's happening when you're doing a wire. Is
Well,
the flux is.
But
and
but also there is you can also mechanically remove that flux by simply taking a fiberglass brush like this and now you can see the brass coming through on that. And when I heat that, if I put the solder immediately on the surface before because heating anything increases the activity of the oxygen in the air, so it's going to oxide much faster. But if I, as you can see, it wets perfectly. If you mechanically remove the oxide or chemically remove the oxide, it will still wet the solder. But that's what we talk about wetting. It flows out and covers the joint.
So what, for novices, so whatever we're soldering, we have to assume that there's oxide on the surfaces that we're soldering.
Typically,
and
yes.
Flux resolves that problem.
Right, but most wire, if we're going to be soldering wires together, typically wires are not bare copper. They're generally going to be tin plated or silver plated. In the case of Teflon wires, typically silver plated over copper. The point is that the advantage of the plating prevents the copper oxides or cupric oxide to form. And all we need to do to solder these two pieces of metal together is to add a little bit of rosin flux right there, and then I'm going to heat this.
And there's solder on both sides.
There's solder on both sides.
And
then
like
I'm going to just simply and I have to wait till it there. Now, it's quite hot, so I can't handle it right this second. But that joint is quite strong, and if you notice, solder hasn't completely flowed over the entire area. But in addition, I can literally put a little pressure on this, like that, and heat. And now it's completely flowed. The actual clamping action allowed it to. It's a little bit too hot for me to touch, but you will see that the solder has flowed completely in, and it also wicked into or flowed into the joint.
Okay, last question. Go really quick.
See, in other words, it's on both sides right there.
Yeah. The two rosins. Can you just go over which one was the better one for this application? The two rosins.
Well, no. If in electrical applications, it's not possible to get in there and clean all of the highly activated paste flux out of there. So you would, if you wanted to use, I just used rosin flux because you can do that. But if I took these two pieces of metal, and I cannot break these apart, obviously, but I can hold on to these and redo the joint, and it will definitely fall off. Just like that. But now you can see how much wetting action took place. And if I can pick this one up without burning my fingers, you can see the effect of the wetting action that took place.
Okay.
Now, if I used, let's just say we're gonna use this fully oxidized piece and another fully oxidized piece that we're going to put right here, and we're going to put a piece of solder. This is called a solder preform. We're literally going to just put a little bit of solder right here, add some fully activated solder paste,
okay, this is flux.
That's flux, and then I'm going to place the solder right there, and then I'm going to take a fully oxidized piece of.
All right, so there's two oxidized pieces with flux in
with
between.
flux, and I'm simply going to clamp
and this is going to work.
Yes, and it will indeed wet out.
Is there possible to heat it too long?
Yes, absolutely.
So you're
you can heat
timing
it too
when you
long
stop.
because, and then the oxides will then form again. So this joint, even though it was fully, it's still a good strong joint.
So you can flux and solder at the same time.
Yes, you can definitely do that. And so it's a very, I mean, it still is balling up. It's not really flowing out here because of the fact we didn't clean it. But if you take and clean it mechanically, it will work perfectly to remove all the oxide. If you mechanically clean it and then add additional rosin flux or paste flux, either one, it's a much better joint. So it's always a good idea to completely clean oxides off of metals that you're attaching. Typically in wires, like I said, they're plated either with tin plating or other plating, gold plating, whatever. They generally won't oxidize, and then you can solder them directly with simple, mildly activated rosin.
Okay, I'm going to ask one more time. I can see both fluxes now. Tell me the name of both and which one does what.
Okay, this is rosin, mildly activated rosin flux. This is highly activated paste flux. This is not to be used in electronics because you need to wash this material away.
And that's what you used to do this?
I used this last joint that I did, I used this highly activated paste flux so that it would break through all of those oxides that were on that surface.
We'll put in the description those two, and if you need to search those or find all that interesting stuff. Okay, Dave, are we done with oxidizing?
Well, we are indeed, but remember, rust never sleeps, and that's because oxygen in the air is always acting on metallic surfaces and other surfaces, but most of all, oxygen is attacking everything continually. I mean, if you have a noisy volume control on your radio, it's because of the fact that the oxygen has been acting upon the contacts, the sliding contacts, and they all have oxide, and that's why it's scratchy when you turn up the knob.
Next time I'm flying on a plane, I'm going to be worried about oxidizing, and I'll be sitting there sweating because I'm thinking the plane's going to go down because of oxidizing.
Well, that's a consideration. That's exactly why they put nitrogen in the tires on an aircraft, because they're made with magnesium, the rims, and they're tubeless tires, and they don't want any moisture or any oxygen, so they fill it with an inert gas, nitrogen. Okay, now we're going to do a simple demonstration of splicing two wires together. Now, this is not necessarily the proper way to do it because generally you need a mechanical strength connection between the two pieces of wire, and then the solder solders them. They don't rely on the solder. We're going to show you just by relying on the solder.
I don't understand what you mean by splice. Splice means to cut.
No,
right? No?
Splice, no, that means strip.
Okay.
And cut.
So
strip and cut are
what
two
does
different
splice
things.
mean?
Splicing is connecting two wires together.
Oh, okay.
That's what a splice is.
I didn't understand
that.
Okay.
And now the first thing I'm going to do is I'm going to use this particular temperature-controlled iron, and I'm going to wet the sponge. What the sponge allows you to do is to clean the tip free of oxides. And then I'm going to, first of all, put on my glasses, and I'm going to put on these. These are very useful for doing precision work. Being able to very closely examine what you're doing makes a great aid when doing soldering. Our actual first demonstration is the wrong way to do it. And I'm going to put this wire here, and this wire here, and then I'm going to attempt to solder these two wires together. I'm going to clean the tip using the sponge right there. I'm going to add some solder to the tip. Now, the reason you add solder to the tip is because of the fact that you need to be able to conduct heat. If you just touch this, it's barely able to conduct heat into the two pieces of wire. So by adding a little bit of solder right there, now you've made a much larger contact patch. And I'm going to hold this against the wires and wait till they get hot. And you can see that this is not working because The upper wire is not really soldering, and then the insulation is melting. It's really the wrong way to do it. If you look at that, the insulation is crept back. It's got a big blob of solder. I'm going to show you the proper way to do a simple splice, but not the way I just did it.
Would that be considered a cold solder?
No, it's not a cold. This is a good joint. But the point is that there's a much better way to do it. So what I'm going to do is I'm going to cut this out. We'll take these out and restrip these. Twist these together. Trim them the same length. Now what we're going to do is we're going to tin the wires before we try to splice them together. We simply put this in the jaw. We clean the tip. We add a little bit of solder. And right at the tip, I'm going to add the solder and there. And you'll see the solder flows right to the other, all the way down, encapsulating them with solder. But you want to move the soldering iron away as rapidly as possible so that you do not burn off additional flux. So what I do here, I clean the tip, I add some solder, I start tinning, and you see it flow up and wick into the solder, and I get away.
Okay, question, how come you're not heating up the wire first before you tin it?
Because of the fact I am heating up the wire. I'm basically adding solder to the tip to get the largest contact patch for the thermal transfer onto the stranded wire.
So the wire is hot.
The wire is hot because you can see it flows up, the solder flows up through capillary action.
Okay.
Now what I'm going to do is I'm going to place these two together, and you will see that once they're tinned, it'll be very rapid. Let me do this a little bit differently. Here we go. There we go. Now, there's solder on both pieces of wire. Now I'm going to, again, do the same thing and watch how rapidly I add the solder, and then they're spliced that fast, and I can move away. Now that is a really good joint, except for the fact it's not mechanically strong, and it will indeed easily pull out, especially if this wire gets hot enough to melt the solder. That's why we generally use a good mechanical connection, and we're going to do that step next. I'm going to cut the wire and strip it again. A little bit longer this time.
So you're saying what you just did was not the right way to do it?
It was not the right way to do it.
Okay, so that was an example of not the right way to do it.
Well, we tinned it. That's the right way to do it.
Okay.
But just splicing the wires together. But we will do a demonstration of a compact splice that does indeed
Okay,
work.
so now we have two examples of not the way not to do it.
I don't understand.
So we showed the first one.
Okay, the first one was, yeah, we have two examples. We have where we didn't tin the wire in advance, yes, and then we did tin the wire. But now what I'm going to do is, again, I'm going to tin each piece of wire after twisting them tightly, clean the tip, add the solder, heat the wire, and the other thing, same thing.
All right, so we're tinning them again.
Tinning this other wire. Clean the tip, add some solder. And by the way, there is another technique that I'm going to show you right now, and that is this. I'm going to do it right on the same spot. I'm going to heat the wire after I tin it. And then there's another way to tin wires. You could just do this. You just,
I can't see it.
This right here.
Right.
I'm going to tin the wires right here. Even though it's already tinned, I'm going to show you a technique that I use quite often. Clean the tip, get the solder, and then flick it. And now it's removed all the excess solder. It's moved all the excess solder so that it's a clean thing. And why do I do that? That's because of the fact I'm going to twist the two together. And so I'm going to heat this again.
Okay, don't flick it towards the camera.
And there it is, cleaned off. Now, I'm going to take a pair of needle nose. After I've tinned it, I'm going to form a loop with the needle nose.
Get in front, get in front.
And another loop. And then I'm going to put these two together. Squeeze one, because once you tin it, the stranded wire will hold itself together. Now we have a really good mechanical connection. Not only solder, but a mechanical connection. Now we solder that together, and that is a strong joint. That is both mechanical and electrical.
Tested.
And oh yes, well this will never pull apart.
Get it in front.
It'll never pull apart. Now what I'm going to show you is the ability to strip and connect and splice zip cord. Now why do they call it zip cord? Zip cord allows you to simply peel it apart. It's used for lamp cord, it's used for all kinds of applications. I'm sure you have plenty of this around your house on like I said, appliance cords and everything else. And it's a very commonly used material. What I'm going to show you, and it comes, by the way, in 18 gauge, 16 gauge, 14 gauge, typically at your home improvement center.
Wait, is zip cord what you have coming out of your lamp at home?
Yeah, it's very typical.
Oh, okay, I didn't know that.
Yeah,
so.
it's a two-conductor material, and it actually also has an indication on the surface to tell you which wire is which. Okay, one is ribbed typically, and one is smooth, and that's for polarity conscious plugs that plug into the wall.
Right. So all appliances, all lamps, everything in the house has
very,
zip
very
cord.
typically use this wire, but many times one needs to splice this wire. What I'm going to show you is the most compact way that you can splice this wire. First of all, I'm going to trim this part that I split apart. I'm going to trim approximately 3/8 of an inch off of that. In that case, I trimmed the rib side. Now I'm going to cut a piece of this cable off, and then I'm going to match it up with this right here, and I'm going to, the rib side, I'm going to find out which is the rib side, and then I'm going to basically put it right here to measure it, and then I'm going to cut just the single conductor and then peel it away. Now I've got rib to rib. It's slightly in the wrong spot, so I'm going to trim it just a little tiny bit.
So you got one long, one short, and they're matching
one long, one short.
They're matching up to each other.
And they're matching them up to each other.
Why?
Because this is how I do this, the compact splice. Okay, right here, compact splice. Now you can see what we're going to do here. I'm going to cut this so I can get in there and strip it. Generally, I use the Miller strippers on this application because you can't get in close enough with the mechanical stripper. So I'm going to use the Miller stripper, and I only want to do literally 1/8 of an inch of exposed wire and twist it, and another 1/8 of an inch of exposed wire.
Why so short?
Because you'll see when I go to splice these together, it doesn't, to make it as compact as possible, you do not want a big joint. You want a tiny joint. And now I'm going to place these in here, and I'm going to tin them. All of these I'm going to tin and make sure they're twisted, meaning the strands are twisted together. And then I'm going to add some solder and tin it and pull it away. You can see there's a little blob of solder. I'm not going to clean these joints, meaning I'm not going to use the wire springiness to clean the joints. I'm leaving a certain amount of solder there on the joint. Now, I'm going to now orient these so that the long one and the short one are lined up. And that's the first thing I'm going to do, is line these up. And then I'm simply going to heat it. I'm not going to add solder here. I've left enough solder to make this joint perfect. I'm going to clean it and simply melt these two together. Then I'm going to take the other and do the same exact thing. And melt these together. Now the reason we do this is so that when I put the heat shrink on, it slides right on over that joint. And the way that I gauge where the heat shrink is, I put my thumb right here and I center it. I center the heat shrink over this, and then I grab my heat gun and I rotate it around, and don't let it slide off of that joint because I want that joint fully covered. And you can see it is as compact a splice as you can possibly make it. It's the rib to rib, smooth to smooth, perfectly strong joint. You can add additional strength by adding cyanoacrylate into the end of this. It'll run down that groove and then glue it so it's even more of a mechanical strength. But this is a splice that I use all the time, and I've never had a failure on this. What I'm going to show you now is the termination of wires and soldering into a cup connector. This is an XLR connector with 5 pins. Now, also the military connectors, very typically are MS or MN connectors, have cup connectors. And this is what the military wants you to do. I'm not going to do it this way to show you the way I do it normally, but I just want to show you the military style. This is what's known as a anti-wicking tweezer, and you'll notice that it has a different size groove for the wire and for the insulator. Now, this is what the military wants you to do. They want you to clamp the wire, which then acts as a heat sink to prevent the solder from capillarying into the wire and making a spot that makes it susceptible to breakage right there. So what I'm going to do is show you how the military wants to do this. They want you to clamp it like this, put it into the connector, hold the anti-wicking tweezer, and then, without tinning the wire, without adding solder to the cup, they want you to solder it all in place. But that's not the way I'm going to do it, because this is very much of a pain to do every single connector. Imagine doing that on everything and making a fixture to hold the anti-wicking tweezer. So we're not going to do that. We're going to show you my method. The first thing we're going to do is fill the cups with solder. Now I'm working backwards to cheat to the camera, so I'm going to put on my visor so I can actually see what I'm doing here. And I'm going to fill this cup with solder. And you can see now there's solder in that cup. And I'm going to do that to every, and then every cup with solder.
Why are you not using flux here?
Because the solder already has flux in it.
Okay.
And now what I'm going to do is I'm going to tin each one of these wires and and leave a little bit of solder on every piece of wire. So that when I install these, there's a little bit of solder right there, which provides us both solder and a layer of flux, because the flux has not been burned off because I don't leave it on. Let me show you what happens when you leave the solder on too long, and watch what happens.
When you leave the heat on too long?
Yeah.
The iron on too long.
See that? See that, what that does? It leaves a solder tail like that, and that's because we no longer, and we've also melted the insulation, okay? But that's not important. What we're going to do now is we're going to show you how I terminate these connectors. I simply hold this wire and plunge it into the connector. It works perfectly in this way. Very rapidly and very easily done. Not like the mil-spec version, which unfortunately I can't afford to spend that much time. I can just heat the outside barrel and then it goes right in. Oops, missed that one.
You're fired.
I'll cut this down, re-tin it. There you go. I'll put the last wire in. And now I'm going to take a piece of heat shrink sleeving, and this acts as a perfect strain relief.
I don't think you need to do them all.
And then I heat it with a heat gun. All the way around.
Can the heat gun melt solder?
If it depends on the heat gun itself, but yes, many times they can get hot enough to heat solder. But the point is that now, when this cools, this will actually act as a strain relief. As you can see, it doesn't allow the solder that had maybe wicked up a little bit here, but it doesn't allow this to bend. So I've always found this to be the most effective means to prevent wire breakage because of wicking of the solder into the multiple strands. But you can see it obviously acts as a strain relief, and it secures the connection and insulates the connection all at once. This is a method I've used for more than 40 years of assembling all types of connectors. Yeah, this is a heat shrink tubing. There's many different formulas of heat shrink tubing. This happens to be polyolefin and neoprene. This is the neoprene tubing. It's a much higher temperature, requires much higher heat to shrink it, but it's also flexible and durable, whereas the polyolefin type is a little bit stiffer when it cools down. Now there's also PVC type, and there's also Teflon type, and there's also very expensive Kydex type, and all of those vary depending on the amount of temperature they can handle, etc., etc. But these are just a sampling of the different sizes. You can get them all the way up to 4 inches in diameter for heat shrink sleeving. Now we're going to talk about working with printed circuit boards. Here are some examples of printed circuit boards. This is a fully stuffed one, as it's known. These are unstuffed, except for these small resistors I've added. Just to let you know, this is a single-sided circuit board. It only has foil on one side. This has plated through holes, double-sided circuit board. These circuit boards come in single layer, 2-layer, and multiple layer circuit boards. The first thing that we're going to do is we're going to move this out because we're not going to do the desoldering right this second. And what we are going to do is to demonstrate how I install components in a single-sided circuit board. Whenever I'm working on circuit boards, I always put on my close-up glasses and a stereo visor. The reason is that I'm able to do much more precision work doing it this way. Now, what I'm going to do on single-sided circuit boards is I simply need to make sure there's enough surface contact on the lead. So I simply pull it up, bend it down in the direction of the foil. Simply to improve the amount of solder that's holding in the lead. Instead of on single-sided circuit boards, it's very difficult to have just the little thin piece of solder. Now I'm going to take and clean my tip, and then I'm going to add a little bit of solder to the tip so that it conducts onto the pad just like that. Again, I want the pad and the lead to be fully molten. There's a little bit of solder on the tip of the soldering iron. I add the solder, and just like that. Right here, I'll cheat to the camera so we can do this. Now you'll notice that these are nice, clean, and shiny things. Now what I'm going to do is I'm going to use what's called a mended dispenser that holds acetone, and I'm going to clean the connection and get rid of the flux. And now you can see the connections are all quite shiny.
What if the solder gets on the soldering board? Is that okay?
Well, there's no soldering board. I don't understand.
I mean off of the plated area.
No, it won't flow there. It can't. In other words, if you try to do that, it won't do anything at all. It's as simple as that. Now, the other thing is I'm going to flip this over so you can see I just used, there's supposed to be diodes here, but I'm just using resistors. But you can see that I oriented the resistors the same direction, and that's generally a good practice when you put stuffed parts, that you have all the diodes going one direction or following the pattern on the nomenclature of the board. But this is for single-sided boards. That's how you affix the components in, because of the fact that you can bend the leads over, and then they have a much larger contact patch with the solder and the circuit board itself. Now I'm going to work on the double-sided board with plated through holes. And I'm not going to fold the lead over like I did on the single-sided circuit board. It's not necessary, and if I ever have to remove a component, it makes it triply difficult to get that lead straightened out and back through the board. So there's only a need to simply pull the components up and bend the leads just slightly so that the parts don't fall out. And then I'm going to put on, again, my close-up glasses and a stereo visor, like I said before. And again, you can see how I've splayed out the leads so that the component won't fall out from gravity. But now I don't need to fold them over like I did on the single-sided circuit board, like I said before. Now what I'm going to do is take the soldering iron, clean the tip, which I did. I put a little bit of solder on it, and I hold it on the lead. And you'll notice it takes a little bit longer for the solder to suck in because it literally fills that hole. So I'm going to try this again. As you can see, I'm going to put a little bit of solder there, and it fills that hole. The same thing here. Again, you notice how it's bubbling. That's because of the fact that the solder is flowing down into that plated through hole. And I'm going to show you when I flip the circuit board over, you will see that solder has appeared on the other side of this circuit board. And it's this fast. And you can see why the 031 solder is ideal solder for working on circuit boards. Now I'm going to trim these leads right at, just slide it down. This is why a flush cutter is used for this application. And now I'm going to flip this over, and you can see right where the solder has come through the other side of the circuit board. And it's fully contained around that lead and in the plated through hole. That's the advantage of double-sided circuit boards. Now I'm going to also clean this with the acetone so we can look at those connections. I just let it drip off the corner so I know that it's clean, and pretty soon it'll evaporate, and there you can see exactly how the solder is done, and you can see it on the other side too. Completely clean. Now what we're going to do is the circuit boards that I just soldered, now I'm going to show you how to do rework on those same boards to remove one of the components from that board. First, we're going to work on the single-sided board, and because it's a special technique of straightening the leads, and I will show you that methodology. We're going to start desoldering using solder wick. After that, we're going to be using a spring-type plunger vacuum to vacuum the solder off, and then eventually we will be using this powered desoldering tool. But the first thing I want to show you is what solder wick does when you put it on a circuit board. I'm going to put this solder wick down, and you can see it capillaries into the solder wick.
So that's pulling the solder out.
That's pulling the solder, pulling it away from the connection. Now, in addition, I need to raise that lead up. So I use an X-Acto knife to heat up the lead.
Now is the solder wick the poor man's device? Is that something?
Well, it depends. I use all of these techniques specifically because of the fact they all have different purposes. The upside of the solder wick is it's very fast. It works fairly well. It allows you to clean up the additional solder that's on the board.
So why aren't you sucking the solder there, and why are you using the wick then?
Because of the fact that I'm just showing the wick. Okay. Now I'm going to take the plunger type and I'm going to heat up the connection, and you can see removed a sizable amount of the amount of solder, and I just need to heat this up and straighten out that lead, because that's one of the things when you do bend the leads over, it makes it more difficult. But I'm going to hit this, suck that up.
So now you're just trying to get the leads up. You're
now
not necessarily.
I'm just reheating this connection to get the lead up so that I can take this component out. The last thing I'm going to do is
the solder out of the first two?
Yes, the solder is out of the first two.
Because it looks on the picture, it looks like the solder is still there.
Well, there's some solder, but anyway, now I'm going to heat this other connection, but this is generally not what I use for bent over leads.
So it's heating and sucking.
Right, it's heating and soldering, but again, I have to use my soldering iron to pry up that lead if I want to remove the component. And then this component is gone.
Okay, now you're saying the components are slipped and fallen out, or are they?
The components are now removed.
Okay.
Now I can use.
Let me ask a question. Did they remove because the solder was hot, or it was completely not soldered?
No, I had removed most of the solder.
Okay.
And so what I'm going to do now is use this solder wick to clean up the circuit board, because it works very well for this particular application. As you can see, you just hold it
right above eye on the solder, and it just sucks all that remaining solder and gives you a clean pad, just like that. But you can see I've sort of lifted this little pad right there. And that is what happens when you overheat, especially on single-sided, because they don't have any attachment other than glue onto the...
Are you saying it's damaged now, or is it
Well,
still...
it's if you look right closely, you'll see that I've lifted that pad.
Okay.
Now, it's not the worst thing in the world because I can put another lead in and bend it over and hold that down. But you can see this is very fragile when you have
the pad was pulled up by the thing that sucked it up, right?
No, from just the heat. The heat, when I heated it, okay, it caused that the copper foil to lift from the adhesive that was holding it. Now we're going to use the same technique with a larger board, and I'm going to show you, this is where the desoldering tool is much more valuable because of the fact it's very difficult to use solder wick on a plated through hole because of the fact that it doesn't really get all of the solder off of that plated through hole. In other words, it just takes a long time, and there's no reason to do that. So I either use the plunger type and do this and heat it.
Can't see it. Move that thing out so we can see it. There you go.
Okay, but again, not all the solder is out of there. That's why this is a vastly superior method. I'm going to do it right here. And it literally...
Okay, the solder looks like it's still in there, but you're saying it's out.
Well, in other words, what I can do is I can see when I flip this over whether or not, see that this solder connection right here is not completely done. This is done. That's not done, but you can go on the other side of the board and simply heat the pad and it comes out. So in the case of this technique, using this power suction, you have to wait long enough and but doing rework does require a completely different set of skills because of the fact you have to literally work at it slowly. See, this is not coming out. So what I'm going to do is I'm going to use my X-Acto blade and I'm going to heat this component and heat the lead until it comes out.
But the gun, it is sucking.
It is sucking the solder out.
Like 50% of the solder out. It's out. Okay.
Right, but it's just that it's very difficult to get plated through holes completely free of solder. And you can see when I do this,
Don't hit
I'll let it hold there and suck it. But you see, it's still not. You can see most of the solder is gone. See, these have plenty of solder on the leads. Well, these are almost completely removed. But it's very common to have to reheat the pad, just like that. Now we're going to remove and replace a component on this fully stuffed circuit board. And many times the most common replacement on a circuit board like this are these electrolytic capacitors. They do have a finite life, and the lower cost units last much fewer years, whereas the really high quality components will last quite some time.
Well, Dave, how often in your career have you changed components on a circuit board? Is this something that happens all
On
the
a
time?
continuous basis. On a continuous basis for doing repairs, because we're going to both show an electrolytic capacitor, removing that, versus removing an integrated circuit, which is much more difficult. But
Can you give an example of like what, okay, what's an example of what was not working and how you fixed it?
Well, I use an in-circuit ESR tester that stands for equivalent series resistance. Electrolytic capacitors, as they age, and depending on the amount of ripple current that's injected into the capacitor and the temperature around the capacitor, they have a finite life. And the higher the temperature, the greater the ripple current into the capacitor.
And that's about troubleshooting a circuit board, which is probably another video.
Yeah, it's a whole other video,
okay.
yes. All we're going to do now is showing how to unsolder and resolder a component into the board. This is a double-sided circuit board with plated through holes, so the solder wick is not going to be very efficacious to remove the solder because it just doesn't flow out of that joint. I will show you one time with a spring plunger, and then I'm going to use this other soldering tool. First thing I'm going to do is heat up this connection till it's nice and hot. But you can see the lead it is loose now, okay? And this actually does work quite well if you can. And there's the component, is out. And if you look through the hole, it's a clear hole. So what I'm going to do now is I'm going to put this component back in. Of course, electrolytic capacitor, the polarity is critical.
Bring it down so we can see it.
So we're going to put this back in exactly the same way it came out. So I would be using a brand new component, not the old component, but I'm just showing that component in here. And then I will take the leads just slightly to hold it in place. And then again, clean the tip off, add a little solder. Now, what I'm going to do now is I'm going to remove a transistor using this tool, the powered solder sucker. First of all, I'm going to hold the lead on, get it nice and hot. You have to wait until it heats up the entire lead and the pad and the plated through hole. Now, that didn't work quite well. And you can see I've already damaged the circuit board. This is very critical work and requires great skill to do this. So now what I'm going to do is heat all the leads up and pull the component out.
All right, let's see the component. Let's just show.
This is a transistor that I just pulled out.
Hold on a second. Let me see it. Yeah, turn it so the viewers can see. Okay, so that just pulled out.
Yes.
Okay.
Now, I'm going to use the solder wick now to clean up whatever material I have left on the circuit board. Again, the solder.
Now explain you said you damaged it. Explain what you did.
I'm going to explain it right now. I'm going to show you precisely what I did. And I'm going to clean this with my toothbrush.
So you just fixed it.
Clean this so I can see. No, I did not fix it. I'm going to show you what this. I lifted this pad. That pad is loose. This pad is loose right there. It's very difficult to do this kind of work easily, and it takes a tremendous amount of exercise and skill. Even as after all these years of soldering, I still have a possibility of damaging circuit boards. So the next thing I'm going to do is I'm going to put this component back in, and of course it has to have the right orientation. I'm going to flip this over and reinstall, if I can see it, this transistor. I'm not going to be able to do that easily. There it is. And you'll notice that in putting that transistor back in, I popped that pad up. So now I'm going to have to pull the transistor back out, put the pad down.
So the message here is even though you did damage it, it's fixable, and you're fixing it right now.
Yes, I'm fixing it. And there's other...
It's not the end of the world.
Yes, it's not the end of the world. Although the transistor has come out, but let me flip the board over again and see if I can't get that in there and all the pads in there also. Again, there's that lead. And that lead. And this lead. But you can see these pads are very fragile. Now I can resolder this. Now there is a technique that I use after I damage the pads like that. So if you look, these pads are still loose. See how they float up and down? It's also possible a tiny bit of cyanoacrylate, water-thin cyanoacrylate, and glue the pads back down, because what happens if with severe vibration, it can fracture the thin copper foil. But I've successfully done this even though I damaged the pads. It's very difficult to do this kind of work, and it's not easily done.
So it would be in a working condition right now?
Yes.
Okay.
Yes, it would be in a working condition.
Okay, what do you recommend for our viewers if they want to practice? What are some pointers? Like how?
Well, get old circuit boards from pieces of equipment and start simply experimenting with removing and replacing components.
In other words, a working circuit board, and then if you remove and replace it, and it still works, you success.
Yes, but I'm just saying, I'm talking about getting scrap circuit boards to work on to begin with.
Right.
As you can see, assembling and soldering circuit boards is fairly easy and easily accomplished. On the other hand, reworking and desoldering circuit boards and components out of those circuit boards is a much more difficult task. As you can see, even I had failures on the simple removal of components from these circuit boards. On the other hand, soldering is an incredibly important skill. If you ever want to build any projects using printed circuit boards and any other type of soldering, I guarantee as you build up your skills, you will find a very, very effective means to repair items of all permutations.
I hope this video has helped you in many ways. If you have any confusion about my techniques, please let me know in the comment section. I promise I will respond. I have also left my phone number in the description section. Please call me. If you have a suggestion for a video that we should make, again, let us know in the comment section. And last, please subscribe to our channel so you can be notified about our next video. Thanks again for watching.